So today we're thinking about the question of, can you have a model without data? And it seems sort of trivial, but I think it really hones in on one of the main differences between Bayesian statistics and the traditional frequentist approach. And I think it boils down to something like this. So in the frequentist paradigm, you're going to specify some sort of model, right? It might be a linear regression model. You know what parameters you're trying to estimate. But in order to actually get a numerical value attributed to those parameters, you need to collect sufficient data. And so it's like the whole problem ends up revolving around the sample that I'm going to collect and having a sufficient sample to be able to estimate those parameter values. Whereas on the Bayesian paradigm, I can actually start my model with no data at all because I can specify the prior distribution. So I can give my best guess based on my prior experience, my prior knowledge, other people's intuition, knowledge, whatever it is, everything I know up until this point in time, I can construct a model that already gives me perfectly valid numerical results for all those parameters. And it's only when that model is deemed sort of insufficient for whatever decision-making process I'm working on that I need to now collect data to try to update what those estimates are. And so it moves the center of the problem from the data itself to the model itself. And now the model itself is this living, breathing thing that's representing the phenomenon we're modeling. And we're only using data as needed in order to kind of shape or update that model as seen fit. And so when I start with no data at all, and then I start adding samples, the transition from no data to some data is actually pretty smooth. There's not some huge gap between those two things. It's like this one sample, if I add n equals 1 to my Bayesian model, it's going to, depending on what the prior distribution is, have probably some negligible effect on those posterior estimates. But it's still going to be a perfectly valid model. And now as I add more and more, the data is going to probably influence that prior more. But in the frequentist paradigm, I can't even have a starting point without any data. And if I add n equals 1 data point, that's not going to give me anything. And so I think it's just a much more smoother and sensible way to look at modeling and being able to incorporate all the accumulation of knowledge we have about something and treat that model as, here's our representation of this thing, and I'm going to add new information to it as needed. So I think the last paragraph in this article really summarizes the point. So this smooth integration of and transition from the prior knowledge we incorporate into the model to the information augmented by the data we collect is one reason why I think Bayesian thinking is better suited for scientific modeling. A more natural accumulation of knowledge, erasing the boundaries between what we already know, which should be considered a form of data itself, and hard data collected on a spreadsheet. It changes the way you approach the problem. Instead of focusing right away on the data, which will be exhausted once it's used, you focus on conceptualizing the living, breathing model of the world that generated it, and thus allow data to only contribute to that model as seen fit. And so for the rest of this video, we're going to jump into RStudio and run through the R code to kind of go through how we built these plots and how we conceptualized this article. All right, so we are in RStudio, and all of this code I just copied straight from the blog post page, so you can reproduce all of this yourself if you wanted. All right, so the first thing we do is pull out a data set, and what we're interested in doing is constructing a model for the proportion of patients who have heart disease in this data set. And so this heart disease data set is just coming from this cheese package. And so we're taking a look at what the sample proportion of patients is with heart disease, so 46%. So obviously this is some sort of already high-risk population. pull in our sample size, and we're going to get our typical large sample proportion estimates from the frequentist approach. And so here we're just constructing a typical frequentist 92% confidence interval. And so based on this sample of 303 patients, that we're estimating that the true proportion of those with heart disease is somewhere between 41 and 51%, point estimate of 46%. And that's the frequentist approach using the normal approximation. Here we just wanted to show what do these normal estimates look like in the frequentist approach at a kind of consecutive sample sizes. So thinking of data collected temporally, as if we have this model we estimate, and now we have data that we're going to kind of collect over time. What does our model estimates look like as one sample comes in, 5 samples come in, 10, 25, 50, all the way up to the full data set, just to later see how does this conceptually compare with the Bayesian paradigm as we update our model. And so we're just iterating through and applying our formulas, and then constructing a plot. So now we're looking at these 92% confidence intervals for all these different sample sizes using the frequentist method. And when the sample size is 0, it doesn't even make sense for us to think what our estimates are. Our estimates are nothing. They don't exist because we don't have any data to estimate them with. When we have one sample, each patient either has heart disease or not. It's just a coin flip, right? And so it's either going to be a 1 or a 0. So in this case, the first patient didn't have heart disease, so our best estimate is 0%. And so we know that's not really even useful. And we also know that it's not 0%. And so with one patient added to our sample, no, that's not telling us anything. Okay, so we get n equals 5. Now we start to get some reasonable point estimate. And applying these large sample standard errors, we're getting some really large confidence intervals. And so, we're saying our estimate is 40%, but it could be somewhere between like 5% and 75%. And so not very useful, I would say. And then so as we add more and more cases to our sample, it starts to converge to something relatively useful. But the point is kind of the starting point. When we have no cases, it doesn't even make sense to have an estimate. And when we add 1, it doesn't make sense. And we need something sufficiently large for our estimates to be meaningful to us in some way. So then the next part, we are just starting to think about our Bayesian model. And so we're plotting the density of a beta distribution, and that's what we're using as our prior for what we think the true proportion of patients with heart disease is. And so this is the beauty of Bayesian statistics. We have no data collected, but we can construct this curve showing where we think, based on what we know about the phenomenon we're modeling here, in this case heart disease rates, that we're saying that we think the parameter, the true proportion of patients with heart disease, is somewhere between 20 and 50%, in terms of that's where most of this probability mass lies. And if we had reason to think otherwise, we could adjust this as much or little as we want to capture our prior beliefs, and then we only need the data to update that as it comes in. Now going to construct our posterior distribution from our sample. And so we are pulling out now our actual data that we observed. This was our prior distribution, and now we're saying, okay, how does this prior distribution change? What does the posterior look like after we incorporate our observed data? So here H and N H is the number of heart disease patients in the data set, N is the sample size. So 139 out of the 303. In this case, in the article, we kind of analytically derived what the posterior distribution is. And so we had this beta, prior, and Bernoulli or binomial likelihood. And turns out that the posterior distribution is just a beta distribution as well, that whose parameters incorporate these two summary statistics. For most of the probability mass was from like 20 to 50 in our prior distribution. Now that our data came in, it moved that prior distribution to more so be centered, closer to like 40 to 50%. And so this is, and it ends up being similar to what that frequentist confidence interval gave us. Although kind of mathematically this is a Bayesian credible interval and the interpretations are kind of technically different, but in both cases, once we have this full sample, they kind of converge on a similar result. All right, so this was where the point of the article comes in, is when we start to, again, think of these sequential estimates as, if we think about our data set, we have 303 samples, but thinking about it more so as we have some prior belief, and now we want to update that with data. How does this posterior change as some data comes in, and we might start with just one case, 5 cases, etc. And so we're trying to see what happens as more data comes in. This plot kind of gives the key result. So if you remember from the frequentist plot, point on the graph where n equals 0, we had nothing. It didn't make sense for us to have any estimate there, because in a frequentist model, we can't actually attribute estimates when there is no data. And then when we had one sample, it didn't really make sense. It wasn't informative. It was either going to be just a 1 or a 0, and we know those aren't even reasonable rates to begin with. And so it wasn't until we had sufficient data that we're going to get something useful. Whereas in the Bayesian paradigm, first of all, when we have no data, we have a perfectly reasonable model. It just reflects our prior distribution before any data was observed. And now and I should say these red bars are capturing the amount of probability mass in our posterior between 40 and 50%. When we had no data, again, it's reflecting our initial uncertainty about what the true proportion or rate of heart disease is. Now as we add a sample of 1, right, one patient comes in and tells us whether or not they have heart disease, just inspecting these plots, it doesn't look a lot different, which is what we'd expect. One data point's not going to change our result a ton, so it's going to basically still reflect what our prior belief was. And maybe if we looked at the specifics, there would be some small changes, but I think this transition point here between n equals 0 and n equals 1 is really the key difference, in that we have perfectly valid estimates in a smooth transition from n equals 0 to n equals 1. And now as we add more and more data, our posterior starts to be more and more influenced by that data and converge kind of towards some agreed upon density of where we think the rate of heart disease is.